This is just a quick little reasoning behind the integrating factor for solving linear first order equations. The book kind of just says, here, use this. And I want to just give you a heads up why it actually kind of works. So the first step is we're going to multiply through by this function u of x and see if a neat little pattern shows up after we do this. So we're going to get u of x times y prime. We're going to get, I'm going to switch the order just a little bit, this p of x times the u of x times our y, and then on the other side, q of x, u of x. And the reason that I set it up this way is if we look at the left-hand side and we look at the pieces involved, you can kind of see what's going on here. You have this function, and then it's a derivative of another function. And then you have the original y function, and what I'm going to say is this must be the derivative of this function. So it's kind of like the product rule, first times the derivative of the second plus the second times the derivative of the first, where the derivative is p of x, u of x. So this kind of implies that the derivative with respect to x of this integrating factor, this u of x, is indeed this p of x times u of x. Now there is only one function where it shows up on the derivative side and on the solution of that derivative, and that function is an e function, e to the x type function. And then this p of x must be the exponential's derivative. So we can say that this also implies that u of x has to equal some e function raised to some other x function, say m of x. Could be like x squared or ln of x or anything like that. So when I set it up this way, we get a new idea out of it. And we can set up that the derivative with respect to x of my function u of x is going to equal well, p of x, u of x. But I've already said that u of x is this e to the mx, so if I say the derivative with respect to x of e to the mx is equal to p of x e to the mx, probably getting a little wordy here now, there's a lot of implications in this statement. The derivative of this side, to find it, it's the derivative of the power times the original function. So that pretty much means that the derivative of m of x must be p of x. I might need a new page. So the derivative with respect to x of m of x is equal to p of x. And now we can do a little separation. Integrate both sides, or integrate both sides, yeah. So we're going to get m of x by itself, fundamental theorem of calculus, is equal to the antiderivative of p of x dx. And that's the start of the integrating factor. Now remember, the integrating factor was u of x. Let me clean this up a little bit. It was u of x is equal to e to the mx. And here we have mx is equal to the integral of the p of x function dx. And that's where the book is getting this integrating factor of e to the integral of px dx, because it works, because it creates a product rule. I just thought it was a neat explanation. Here's an example of a linear first order equation, and the big thing here is we have this 2xy prime minus 3y equals 9x cubed. It has to come into the format that we're used to, and if you force them all into the format that the book follows or technique follows, it's easier to figure out the problem. Now there are some cases where you can just look at a problem and solve it, but I don't usually lean that way. I usually try to get it into the correct format and then solve the equation. So here the problem is y prime is supposed to be by itself, and it has this 2x in front of it. And there's a quick fix to this. Just take everything and divide by 2x. That'll isolate the y prime. Now I did this problem 5 minutes ago, and I made a huge mistake. I did this really quick, and I wrote down 9 halves x over here, and I solved the entire problem. It came out wrong. So be really careful about every little piece that you do. If you make one small mistake, the rest of the problem does get a little screwed up. So here the 2x's will cancel, and we'll just get y prime minus, and I'm going to write this as 3 over 2x y. So we have a p of x piece and a y piece, and they're separate from one another. And this little piece here, this p of x, is going to become really important. Is equal to, and over here it's going to be 9 halves, and x cubed divided by x is x squared. So let's see, 9 halves x squared. All right. So now the technique says, well, we need to take this p of x and create an integrating factor out of it. And to create an integrating factor, it's going to be e raised to the integral of p of x, whatever p of x is there. This integral here is not going to have a constant of integration. This is really technically just an antiderivative. So in this case, it's going to be e raised to the antiderivative. The sign's going to be taken with this, so it's actually going to be negative. I'm going to pull the constant out because with integration you can always pull constants through. So we'll get negative 3 halves sitting out front here. And on the inside we're going to be left with 1 over x. That x cannot be pulled to the denominator. It has to stay in the denominator. And dx. And the antiderivative of 1 over x, nicely enough, is ln of x. So we'll get e to the negative 3 halves ln of x. All right, now the e and the ln are inverse functions, and we really want them to be touching one another, so the way I say it is they go poof. So this negative 3 halves has to move, and we can use a law of logarithms to move it into a power position, because a number times a logarithm is the same thing as a log of that thing raised to a power. That's a neat little law. So this will give us e to the ln of x raised to the negative 3 halves. And now that the e and the ln are next to each other, they kind of go poof, and we just get this nice algebraic expression. So this is going to be our integrating factor. We're going to multiply our equation by this to produce the product rule. So this is going to give us x to the negative 3 halves times y prime minus 3 times x to the negative 3 halves, I'll simplify later, over 2x, and this is all times y, is equal to 9 halves x squared times this x to the negative 3 halves. All right, so simplify, and we're going to get x to the negative 3 halves, y prime, minus, let's see here, if I bring the x up, that would be negative 2 halves, which would make it negative 5 halves. So this will be 3 halves x to the negative 5 halves y is equal to 9 halves. A little common denominator, this would be 4 halves minus 3 halves, which leaves a half. Okay. So this is all perfectly set up for the product rule now, because we can look at it as first times the derivative of the second, and the second times the derivative of the first. Now the derivative of x to the negative 3 halves is negative 3 halves x, and you lose a power, negative 5 halves. So let's take this over to another page so we can finish it. And just the recognition that the left-hand side is the product rule, we can use that fact to write it quickly. This is going to be the derivative with respect to x of the first function, which is this x to the negative 3 halves, times the second function, which is this y. And the product rule would pop it back up into what's up here and under the red. And the other side doesn't get affected yet. 1 half. Okay. Use a little bit of fundamental theorem of calculus and moving a few pieces around, but technically it's just, integrate both sides. And then this side we're just going to attach the dx. So here the d, dx, and the integral are going to fundamental theorem themselves away. And the left-hand side is going to have x to the negative 3 halves y is equal to, and then we're going to take the antiderivative of this side. So the 9 halves is going to pull through. The antiderivative of this, we have to increase the power by 1 and divide by that power. So if we increase it, it'll be 3 halves. If we divide by it, it'll be 2/3. So we're going to multiply by 2/3, and it'll be x to the 3 halves. Now this is different than the integrating factor. This is a true integration where you're going to have an integrating constant, where the other one, the integrating factor, just was an antiderivative. So we really, really need this plus c here. All right. The next step would be, solve for y. So divide everybody by x to the negative 3 halves. Now I'll show this step. X to the negative 3 halves. X to the negative 3 halves, and including the c. This is important. You can't just leave the c as c. It's got to be c divided by this x to the negative 3 halves. So we're down to our solution, which is y equals, the 2's cancel, 3 goes into 9 3 times. X to the 3 halves divided by x to the negative 3 halves would be positive 6 halves, which is 3. So this would be x cubed, plus, and I can bring that negative exponent up, so it would be x to the positive 3 halves. And there's our solution. And you can check your work by taking the derivative of this and plugging it back into the original differential